Oh yeah, welcome back. So let me help Jody to finish the second part with a new hairstyle. Because my previous hair disrupt the microphone. So yeah, so I'm feeling much clearer. Because my brain feels super cold for some reason. And yeah, let's wrapping up seed application about ODE NATs on the supervised learning. So what do we have? We're still solving the MNIST problem. We're trying to classify the hint digits writing in 10 numbers. So with the previous one, we have the ResNet. So this is like a regular ResNet. We have 30 layers, and that's the performance about the ResNet. We do achieve a test error about 41%, which is super good. However, we do have a very high memory, which is OL. And L is the number of layers in the ResNet. When we do replace the ResNet with the ODE NAT, we do see we achieve a similar test error. But the difference is we improve the number of the parameters and also the memory. And the most significantly is the memory now is only constant, which will be a super brilliant work. Because usually it takes a long time to train the ResNet. I do see the benefits now about using an ODE NAT. But the reason why the ODE NAT have less parameters, it might be because when we define the G function, it's only calling one ODE blocks or small neural nets. What we are trying to do, we're trying to updating all the zetas or parameters instead of using 30 different res blocks. So that's the improvement about the number of parameters. Also, the memory is saved because we do not save the intermediate activations results. We do actually trace back the joint state whenever we do the evaluation. So that's a big improvement in the memory and still achieving the same level of the test. So there's a question how deep are ODE NAT? That's how we compare between different architectures. The thing is there's no formal depth definition in the ODE NAT. So the thing you can understand about ODE NAT is the number of evaluations in the ODE NAT will be a similar word in the depth in the ResNet. And I want to say evaluation is the output of the dynamics G function. And the G has different components about the state and the parameters. This is the results that I generate from the paper. We do see the dynamics become more demanding to compute during the training. And we do see the models is getting very complex when your training goes on. And when you see the training epoch from 25 to 50, there's only 2.5 number of evaluations, but you're around 11 evaluations in the first 25 epochs. So we do see the model is getting complex. But the downside for the ODE NAT is you cannot control the time cost of the modeling during the training. You can just let it go and let it run for several nights, and then you get a model. So this is a thing you cannot control in the supervised learning. But we do have a benefit, is that you can control the time when you do testing. It is when you do the testing, you can input a tolerance of error. Suppose so in this picture, my tolerance of error is 10 to the negative 4. So I do have very strict error restriction. And now my number of evaluations range from 50 to 80. But if I loosen my tolerance, I do require less evaluations from 40 to 60, and with a loosened tolerance of the error. As you move on to loosen more I'll still move on to give more freedom to your ODE solver. You still achieve a very good estimate. See, so even you lose your like arrow to the 10, it will still give a red range of the number of evaluations and its arrow. So we do see ODENet can do a pretty good job, even you do not set properly to your error tolerance during the testing period.
What are the blobs that you're showing? They're just running the thing with different initializations?
Yeah, they're just testing in the testing period and see how many evaluations. Because like the more evaluation you have, the longer it takes. So it wants to see if you can do a control of number of evaluations you're testing. And if you want to test your time to the test set, so when you see the ODE solver here, the difference is you can have an arrow. So this is a tolerance on your test set. So you can have a hands-on control in this stage. So move forward. So there are two stages. One will be the reverse and one will be the forward part. We see the number of evaluations in the forward is almost like double the number of evaluations backward. But why the number of evaluations backward is much less than the forward? That's credit to the joint sensitivity method. Because with that token, it helps you save lots of time and the space to calculate the rest of the gradients. So that's why the number of evaluations is much less in the backward than the forward. Sure.
Just a quick clarification. If we are not doing any back propagation,
yes.
So in an ODE solver, we always can control the error because there's a differential equation which you put everything in and you see which direction you are going.
Yes.
But the reason we needed backprop is because you always change on the hidden layers the values, knowing what the final output is. So I don't understand that making the whole thing very continuous, taking very small steps. How can we make sure that the path we are taking is correct if we are not taking into the final information, which is the output? That's the backprop value. So how is this field, the vector field that you're generating is so accurate and does not use the final layer's results?
So how this works is like you actually visiting the ODE server twice. So when you go from the input, you have HT0. You visit your ODE solver, and it will give you HT, right? So this is one time you visit ODE solver. But when you backward, you do need to visit another ODE solver, which give you the adjoint state. So adjoint state has some benefits. So that's why in another ODE solver, it needs less evaluations to check the results. So it's
I don't know the results on the layers, right? To begin with, I don't have any information on what the layer values will be, or do I?
Yes. But you are free to print out any HT. Because like whenever you, like back to a previous one, when you draw the track of HT, so you just throw your H0 function. But you can handle, you are free to do any investigation about HT during the process.
Okay, I think I'm beginning to understand what you're saying.
So yeah, so the major contributions for this paper is they introduce a new way to tackle the supervised learning, but still like the time cost in the training about the MNIST problem is not very good, but still achieve similar test error. But we do see some benefits. So first of all, the constant memory cost is the biggest benefit, I think. And the second of all, I think, is like you did not need to specify the depth, the structure about the neural nets. You just throw everything, leave it to the black box. Then you will get a close test error within your training process. So we can replace the ResNet somehow with the ODENet if you are not busy and rushing home. So you can just leave it running for several days, and then you get the results. But like in the paper, they do say like ODE nets can help a lot under application like irregular time series data. For example, for those medical record, like which was reported in the random times. So this is a time series data problem. And with the ODE net, it will be super helpful and powerful because ODE net can dealing something with time. And another application about flows, normalizing flows, which it sounds pretty unfamiliar to me, but it's a very good topic to deep dive. The discussion. So after I read the papers and talk with my facilitator, Helen and Lindsay, we derive these two discussion points. So the first of all is like, how do you actually regularize the dynamics, the function G, to need fewer evaluations? And the second of all is like, how do you actually compare your ODE net with other architectures? Like, is there any bias that were introduced if you do the evaluation between different architectures? I have no answer. So hopefully, if you got any answer, we are open to discuss.
Is that, if the second question is coming from one of the things that I
Yes.
asked, I was also wondering about, so they bring up in the paper the idea that there's no way to specifically conceptualize depth because you don't have like a certain number of layers. And so if you want to compare the accuracy or effectiveness or functionality or whatever of a neural ODE, rather to a neural network, they use things like memory or number of parameters. But I was kind of wondering if you wanted to implement it yourself, what would make the most sense to you as a practitioner to figure out whether this was an effective solution for you, and whether it might be like accuracy at time of evaluation given a certain amount of time that you have to make your prediction or something like that. Like if you can't think about depth and you can't think about like, if you don't have the same structure to compare to neural networks, how do you think about whether this is something that you'd want to take up?
Yes. But that's why like when they do the application to the MNIST, so they do compare the training time. That's why they prefer still using the ResNet rather than the ODE net. But when you go to the problem like time series data, which might be very tricky to handle by the regular neural networks, that might be the only approach we have.
Yeah, can I point out something else about the time series data? So, okay, so when they go into some detail, I want to back up, and maybe this is being impostery and whatever, but I don't really have the math background to totally understand all of this, so I was hoping that someone might have read it and understood the time series aspect of it to be able to flesh it out more. But it's the time series that they're talking about, that idea of time, is different from the idea of T, that is the different layers or the depth of the networks. The idea is that if you want to deal with data that is coming in at a regular interval, so maybe that's medical data, or I've worked with manufacturing data where like something happens with a sensor and it records the change, and then something else happens and it records the change, but you're not querying the system at regular intervals. And the way that they approach this is something that is related to variational autoencoders and a generative model, and they're learning the pattern over time in a way that is more complex than just like a sequence. So I have a whole bunch of questions around that, if anybody has read it and think about it. Yeah. I don't know if I can answer the question, but I'll try.
No,
yeah.
Just clarification. So you said the part that I didn't get was the variational autoencoder part, but before that is like, it seems like you're saying that the time is continuous, but in order to have an idea what's going on, they're sampling at certain times that some change is happening. And did I get it right? Or
if you have a problem where your data is coming in at irregular intervals, the way that you might address that with RNNs is to concatenate your data with something that has like the time until the next sampling point, or the time since the last sampling point, or something like that, to try to take something that is not a regular time series and make it into something that you can feed into an RNN as if it were. Right? So you have to like add extra information about time since previous sampling point or something like that.
If your data is continuous, correct?
If your data is continuous but not being sampled consistently.
Correct.
Yes. Yeah. So not like language, but like yeah. Something where there's a time element, but you have inconsistent sampling. So they have an approach to dealing with it that uses neural ODEs that I can't explain the generative part of it. Maybe you should read it and explain it to me.
I kind of get where you're going with the generative idea, but I also don't have any background.
So what are they exactly, not exactly, but what
I'm not going to be able.
Generative part for?
I'm not going to be able.
I should have read it.
It's like understanding. When you're understanding the sampling points over time, it's I think analogous to understanding the distribution of something.
Yeah, right.
So it's like the shape of it. Yeah.
I think I have. I don't have an answer to your question, but I did try to get that point too, and I think I have one element of it, which is that normally when you're trying to solve a machine learning problem, you have an input. I'll call it X, which I think is consistent with your talk. Input X, output Y, and some function that maps X to Y. And this F is parameterized by the neural net. But it doesn't have to be. You're essentially assuming that there exists some F, and then you're trying to find a good approximation one way or another. I think what they're doing is they're saying, I don't want to parameterize this F. I want to pretend like this F is the solution to that integral equation. And instead, inside that integral, there is some other function, which we call g in this case, which is a different function. But I don't really care what this function is, because I don't even know what f is anyway. What's the difference between learning f or learning g? So what they're trying to do is they're saying, all right, I still have my x, I still have my y. And the backpropagation, by the way, does use y. It is not true that it doesn't use the output.
Yeah.
It wouldn't know otherwise where to go. So you still have x, you still have y. But now your function is kind of an integral of something else. And then you have to do all this black box magic to go from the real world where the f lives to that derivative world where the g lives. Because you have to change worlds. It doesn't operate on the actual data. It's a vector field in some space, which you don't know what it is.
That's the key part of this paper, that they are doing continuous backpropagation on this element A, which is another differential equation, which is the adjoint. But for some mathematical or numerical reason, that's easier to do, and the field that we are seeing is of that. So it's doing the backpropagation. So ATN is like almost like what is our Y, what's at the final output, and from there they are backpropagating it. So I think that's the main thing of the paper, that they are doing continuous backpropagation, not on the real variables. Yes.
But what you're saying makes sense with regard to the paper generally, but that's not the specific time series part.
So now if you want to go to time series, you're actually doing the same thing. So suppose we have, what's a practical? For example, we have monitored data from pulse, breathing, something of a medical patient, and this is your data. And it makes no sense to measure, let's say, the temperature of the patient at every second, because someone needs to walk and actually measure the temperature. But you can measure the pulse in continuous time, like every 15 or 16 seconds or something like that. And so the sampling rates of different variables are different. One way to approach this problem is to indeed do what you've just suggested, is to just resample, like say, okay, why this sampling interval is, let's say, 2 minutes or 10 minutes, so I'll resample everything to 10 minutes and I'll average around. Another way you could do is you can say, I will pretend, just like they do, that there is some function underneath, the continuous function, that is actually producing these variables. in that case, you could use something like a Gaussian process to approximate that function. It's a mathematical probabilistic trick to get a Bayesian estimate of a function, which will produce you values that you can sample whenever you like. Their idea, I think, is to pretend that there exists this vector field, which now, instead of being a vector field, is actually just a field of all these sampling values. So if you had the luxury of measuring everything anytime you wanted, you would have this field G, not F, G. So their solver is capable in principle of producing the solution, the actual solution from X to Y, without sampling G too often. On the other hand, their solver is adaptive, which means it has to pick when it does the sampling. So if I had this patient and I had access, and I could say to the nurse, hey, you're going to measure it now. And then I can wait for another 15 or 20 minutes because I'm confident that my prediction, my ODE, is actually good. And 20 minutes later, I'll say, now you measure it again. And there is a change, and I did not predict the change. So I'll say you measure it again, like 10 seconds later, and another 10 seconds later. These are the points that you've seen on I think, one of the first slides that you've shown us. In this case, I could understand how their method works. But there's still a gap between what I've just described and what I think you've asked about.
I think
can't bridge it completely.
the way that you described it is actually the way that the paper authors describe it. So you're viewing the generative aspect of it comes from looking at the learned model and its outputs as being representative of the distribution. So that's the generative aspect that they're coming up with. So it is actually in line with what you said.
The only thing I wasn't sure about though is because at the end you were talking about the different points, the different points in that vector field being like the different sampling times, and I think that is, until then it was good, but I think that's mixing like latent space with actual data space. Like those points are not, that time that is in that vector field image, that t is not the same as like actual time, like, okay, measure the heart rate, measure the heart rate, measure the heart rate. So I think, does that make sense what I'm saying?
As far as I understood, there was no difference between latent state and the real world, but the two worlds I call it, because you can always go back and forth using the solver. But I could
You can go back and forth, but like they talk about in figure 9 is showing, I don't know if this is anyone else is looking at it, but like data space trajectories as opposed to latent trajectories, and I think those are different spaces.
What page is figure 9?
8? But someone tell me if I'm wrong. So like figure 1, which is the vector field, and you have the different points at different points along the vector field, that's not the same as sampling at different time points. It's like sampling within the latent space as opposed to the like data real world space. But that might be, maybe we should go back to the discussion points. I may have just sent everyone on a tangent. I think the only point I wanted to make there was that that concept of time is different. Like the t, the concept of t as depth within the neural ODEs is different from the concept of time in a time series.
So hold on. So I promised somebody to ask a question here back in the end. Did you want to ask your question? I stopped you during this session. Not interested anymore?
What was the question I asked?
So you asked about wavelengths.
Something like, can you come forward?
Yeah, please come straight.
Okay, so I'm not a machine learning expert.
Not yet,
thing.
not yet, not yet.
Keep coming.
Keep coming?
Keep
Okay,
coming to the table, yes.
Good.
Okay, perfect.
Beautiful.
So everybody can hear me now?
Should I?
Yeah, no, it's fine.
That's good.
Okay, so what I asked was, I'm not a machine learning expert, but you know, I heard about wavelet neural nets and recurrent wavelet neural nets. So I was wondering if you can, if the changes between, say, the layers of the, like how you would apply, say, like a wavelet neural net to something like this. This is like, I'm just thinking how you would do that. Or if this, if G represents those wavelet neural nets. I think that was my question.
I'm going to slip in, oh, somebody has an answer? I'm going to slip in a quick answer,
yeah.
and then people, if they like to, they can take on, or we can move to another question. I think it's a parallel way of doing things. So even ResNet is parallel to this one. If I understand it correctly, because you're comparing with ResNet, you're basically, you have a neural net, it's just its training mechanism is different, and counts on continuous space. So I'd say it could be just a parallel method. What you're saying, I remember reading about it, but I don't exactly remember the details. It seems that there is another, that's another method that you apply to continuous data to learn.
Because like as my understanding with the wavelet neural net is that when you decompose a wavelet and into transformation, you break it out into different frequency components. And those frequency components, they become part of the hidden layers inside of this neural net. So say these frequency components, the coefficients, I think, that they're in the wavelet neural net. So if you applied, say, the ODE, where the changes in between those layers, or the changes between each wavelet composition, because they use wavelet neural nets for data compression, like JPEG 2000. That's what they use it for. So, I mean, maybe there's an additional efficiency boost in that data compression.
I think the difference between like ODE nets and wavelet neural nets is like wavelet neural nets are meant for completely continuous signals, right?
Yeah.
Whereas these are, I think the example they give on one of the abstracts I read is medical records, not like medical sensor data, but like a patient comes in and they get a checkup and you get a data point, and then 2 years later they get another one, and 6 months after that they get another one where it's completely irregular and pretty large time scale as well. I think that's kind of the time series aspect that these are approaching, or they're saying that they approach. I don't know if that's kind of the direction we're going, or if that helps.
Yeah, I mean...
It doesn't seem to touch this one, to be honest.
Okay, I see. It's totally completely different.
Yeah, it just
They're completely different.
Yeah,
Okay,
hey,
hey, that was the answer.
I'm also not sure of the wavelet neural net, like how you would even be able to incorporate all this, because what you were kind of explaining was just the basic idea of a wavelet, like taking it into the frequency domain and all that stuff.
Which you don't need a neural net for.
Pardon me?
But you can just decompose with
yeah, absolutely.
Fourier transform.
Absolutely, you can do an STFT or whatever. So the wavelet neural nets, the whole idea is actually quite simple. It's just instead of a regular neural net, you change the activation function to a wavelet, so it might be selective to those frequency components, and at that point, you know, your neuron's turning on. So I think to bring that here, it may be possible, but I think that those calculations would be very computational, maybe even intractable, considering the actual closed form expressions for wavelets.
Just a note on architecture comparisons as a whole. This isn't a drop-in for anything other than a ResNet, actually. It's not a drop-in for anything that requires dimension changes, essentially. It's not a drop-in for like a multi-layer perceptron, so I don't think you can really liken it to the structure of a wavelet network at all. Yeah, it's like strictly drop-in just for ResNets.
All right, that was our collective attempt.
Well, my question is probably, you know, a very specific case of Lindsay's, well, general use case. For this paper, my hypothesis is that it compares to a residual network full of fully connected linear dense layer. Am I right?
You're shaking your head. It feels like it. Because the way they show it in the paper, like here we're not showing the depth, but they're showing the depth, and there are multiple vectors. So I'm guessing what he said might be true.
The paper doesn't mention anything about convolution later, anything like
Oh, you can actually check their GitHub, so they do have the application. So when I do check their code, it's like, so they define the ODE small block, the function G, is a traditional 2 layers convolutional plus activation. Yes, they do like that. And they're using that block to throw in the ODE solver for the initial talk.
But the end result is no longer convolutional at all.
I'm not sure, but I remember the input.
Well, this is just my intuition. For convolution and the way sharing works, you have to make sure that the t's are identical. And in this case, you have a part of the field applied to one patch of the image, and it results to a t, and the same patch applies to another different patch of the image, and it results a different t. It results a different t. So what's the point of sharing weights between different t?
Sorry, T means the number, like the dash.
Yeah, exactly.
So I do think the ODE net here can be understood as a skip for a series of the ResNet block.
Yes.
So you only keep the first one.
Yes. But in the meantime, well, the convolution generally means, well, part of the, different, different part of this field, their weight should be shared, or at least preserve some kind of self-similarity. And in this case, because, different filter applied to different patch of the image results in different depth. So, well, there's no point in maintaining similarity between the, the dynamics at different t. So in this case, it seems like, it just doesn't make sense for any convolution to work here.
I do get your point. It's like it doesn't think it makes sense to using only small neural networks to maintain all the information according to images.
Not small, but a self-similarity.
Yes.
Well, in the, in the definition domain of the input function.
But you still need to do the evaluation, even though you have a very small amount of ODE. And they do receive a similar test error with only a small ODE block. So in that sense, like although we are showing something unreasonable to a black box, but the output turned out to be pretty good as our traditional convolutional networks. But then therefore it's a kind of way to prove like it doesn't actually need to be different cleaning method for different images.
It's probably because their training data doesn't have a lot of translation.
Yes, I do remember they do decompose. They're trying to simplify the input of the data.
Oh.
Yes,
Okay.
they do decrease the size of the images and do some transformations.
Okay. Then I assume the end result of training is probably not convolution. Well, it's...
So I just want to add something, and if that doesn't directly relate, we'll move on. It's my understanding of your question. So you're saying that CNNs, you share weights, sure.
Yeah.
And then you're saying, why would you share weight across time? Well, you do that all the time. So like in NLP, you do that. And in other, any sequential data that you use CNN for, which you...
sorry, I'm just talking about feed-forward case for a single image. Of course, weight sharing across different time is like very important in our... but in this case, let's confine to depth, not time. So in this case, yeah, because...
It's in depth.
Yeah.
It's hard to make sense of.
So I feel like it's probably related to Lindsay's case because in both cases where you don't have the freedom to choose the sample point on your own. You're always subject to some external force, and in this case what's the next T is like is a force of nature.
All right, thanks very much. Any other questions?
Yeah, so how do you apply this? Like, what would I use this for? I mean, like, playing English, like, what would I use, like an ODE neural net for compared to others? Where would it perform the best?
So far, it doesn't beat the ResNet, and
Oh, okay.
Doesn't it with some?
Well, I guess you said for the cases that you have irregular time series.
yes, irregular time series will be a good application.
Yeah, it beats the RNN.
Like different sampling frequencies.
So also it has a memory advantage, right?
Yeah.
Yes.
So it has a memory advantage and it has a dynamic architecture. So you don't really have to bother to define your architecture freehand and have it constant. So in cases where you don't know what's your depth or you want more of autonomy, then you can use that with regard to your architecture.
Like when it sits in memory and everything, is that like, does it just like blow it up and then?
So it doesn't grow with L as with ResNet, right? With the size of the layers.
I will be honest. I don't even know what a ResNet is.
It doesn't matter. So what matters
I'm
is that
connecting all the dots. Every session I go to, I learn something new.
No, that's good. It doesn't grow with that variable L,
Yeah,
right? It's constant. I think that's.
So is it, just to follow up on that, because I'm not super clear on the reader. So when you say L, is L proportional to Tn minus T0? Like is it, like the number of layers you choose, is it like how long you're integrating your ODE essentially?
Well, and that's L is for ResNet, right?
No, I understand. But like, let's say you have an ODE and you want to solve it with ResNet.
Right.
So L, is that like how long you're integrating your ODE, or like how do you choose L?
It's
That
how
goes
often
back to the.
how often it takes a point, how often it does a forward pass.
I think that gets back to that question of like how do you think about depth and how do you compare between? Can you go back one ahead where it shows the ODE, just in the yeah. So in that case, the ODE net doesn't beat Res. I mean, it's like almost the same, maybe, but it doesn't beat ResNet. But then you're using like a third of the parameters, and I'm not really sure what that means for actual training time. Like they have memory as well.
So a lot, yeah.
So if you decided to use 0.3 million parameters, do you end up getting a better, right? You might, and then one of the points I make in the beginning of why this could be a useful approach is because you can determine your accuracy at training time and then reduce that accuracy at testing time. So if you want to build a super accurate model, but then you want to run it somewhere, like I'm guessing like on a phone or like somewhere offline in a plant that doesn't have internet connection, like I don't know what it would be, but somewhere where you need to make a fast decision with less power, then you can control the accuracy at that point. So I think it lets you put more effort in the front end and then have quicker estimation or evaluation at the back end. Also to the question of why is it, like where would this be useful? It seems like that time series thing is like groundbreaking and super helpful. Like I really want someone to tell me why it's not like just like mind-blowingly useful.
It's like when certain events get triggered, like at very irregular times, you can't estimate exactly when those like events occur.
If you want to make prediction on that, you often have to interpolate or figure out some other factor to estimate how often your point has been taken. Like you have to do like workarounds. And when they do that with an RNN and then they compare it to the ODE option, the ODE option like blows it out of the water. I mean, it depends on like how many evaluations you have and how many observations you have and stuff like that. But that seems to be really exciting.
So as compared to RNNs.
Yeah.
If you guys have a question, I encourage you to ask. If you guys have a question, I encourage you to ask, because this is the point of the session. Did you want to ask a question?
We actually got bored, so we were looking at our phones.
Okay, so about the RNN, we're almost done. So about the RNN, first of all, like, so, are you saying also that so you said that it beat RNN? is this, first of all, what architecture do you use for the RNN?
That's the part that I need you to read it and explain it to me.
Okay, so let's talk after.
Okay.
Are you also saying that it's computationally more efficient? Because RNNs aren't really known for efficiency.
That's a good question. I don't know.
Okay, so maybe
Yeah,
those
that
are the
could
things
be that could be one of the trade-offs. That's
Okay,
true.
we'll talk after.
Cool.
All right, I'd like to end this. Oh, you have a question? Sure.
Yeah. So in terms of the MNIST dataset example given over here, they do talk about the improvements in terms of number of parameters as well as memory, but do they talk about the time taken by the ODE solver versus the Red Hat?
See, they do mention.
In terms of training?
It takes way more longer.
Okay.
Yeah, it does.
To receive this test output. Yeah. But that's only for the training period. But in the test period, you have some freedom to control the time to training by setting a good tolerance, but still achieving a pretty fair model.
So compared to hyperparameter search, over there you're also like your time was really constrained because every time you change your hyperparameter, you should train the entire model. So comparatively, this seems like a go-to, but I still need to look better into it.
I do have a quick question. In one of the sections in the paper where they say, hold on, I lost it. But basically what they say is the number of depth is analogous to the number of evaluations the ODE needs to make. They also say that everything about the model architecture is left to a decision for the ODE to make. So like how much, is there like no tuning that's involved in like you make an ODE model for a specific data set and you usually just run with it? Or is there anything else that you need to tell it to control things like the number of parameters?
You can control accuracy, right? Like what your limits for your tolerance.
Okay, so
for
the higher the tolerance, the more evaluations it needs to make, the bigger it gets.
Lower the tolerance, the more right? Right?
Lower the tolerance to error. Yeah. Okay.
All right, beautiful. Thank you very much. Let's thank the speaker.